In this section, we're going to be going over optimization problems. So previously, we have been finding extreme values. We take the derivative of the function, we set it equal to 0, and then we solve for the variable, and these can help us find our extreme values. So this concept actually has a lot of practical applications. For example, if a business person wants to minimize costs and maximize profits, a traveler wants to minimize transportation time. And these types of problems would be called optimization problems. We're trying to maximize something or we're trying to minimize something. So here are the generic steps here for optimization problems. First step is just rereading the problem a couple times and understanding it and seeing what's given and what is the unknown that you're going to be solving for. The second step is going to be draw a diagram. Typically, this will help you visualize what is going on. Step 3 is going to be introduce notation. So just assign variables. And that was pretty much the first 3 steps are kind of like setup. And now steps 4 and 5 are what you're actually going to be doing. Typically, what we're going to be having is we're going to have 2 equations. These are going to be equations that we have to figure out. And we're going to be maximizing or minimizing one of these equations. So whichever equation that we are maximizing or minimizing, we need to rewrite that in terms of one variable using the other equation. And then taking the derivative and setting it equal to 0 and solving. So the 2 types of equations have a name. One equation is called the constraint equation, and the other equation is called the objective equation. So the constraint equation is going to have some sort of constraint value. For example, the question is going to say something like the perimeter has to be 50 yards. There's a constraint there. And for the objective equation, this is the equation that we're going to be maximizing or minimizing. For example, find the largest area. That's the equation that we're going to have to take the derivative of and set it equal to 0 and solve. So after we take the derivative of the objective equation and set it equal to 0 and solve, we need to verify that our answer is a max or a min using either the first derivative test or the second derivative test. Okay, let's go ahead and do some examples here. So a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So I'm going to start this off with a picture. We have a straight river, and then a farmer wants to build a fence, a rectangular field, where one side of this rectangle is the river. And then we have this fence, which with the river creates the rectangle. And once we have this picture drawn, now we can start thinking about the equations that we're creating, the 2 equations that we need, as well as the variables that we're going to be using. So the 2 equations are going to be perimeter and area. Right here, we can see that we're trying to find the largest area. So that obviously has to be one of our equations. And we know perimeter has to be the other one because we have 2,400 feet of fencing. So that actually represents the perimeter of the fence. Okay, now let's go ahead and label the rectangle that we have with some variables. We know that if we call this side x, then the opposite side is also x because it's a rectangle. The opposite sides are congruent, and we can call this side length y. Okay, so now let's go ahead and take a look at our 2 equations. We need a perimeter equation and an area equation. We know that the perimeter has to be 2,400 feet. That's our constraint because we're told that it has to be 2,400. So what we could do, which I'm going to erase in a second, but what we can do is start with saying the perimeter of this field with the fencing. Perimeter, we add up all the sides. That's x plus y plus x, or 2x plus y. And since our perimeter has to be 2400, I'm going to replace the p with 2400. And I'm just going to move this over. That is our constraint equation. So the constraint equation is the perimeter equation in this case. Next, we need the objective equation. So the objective equation is what we are actually going to be maximizing or minimizing. This question, it's always going to tell us. It tells us that we want to find the largest area. And that means we're maximizing the area. So maximizing the area, the objective equation is going to be area equals, so A equals the area of this rectangle would just be length times width, in this case, x times y. So the objective equation's variable always just stays the same. Constraint, you have to replace with whatever the constraint is. Okay, so this is pretty much half the battle here. Now what we want to do is recognize we have two equations with two variables. We need to rewrite the objective equation with one variable, and we do that using the constraint equation. So from the constraint equation, we solve for one of the variables. If we subtract 2x on both sides, we get y equals 2,400 minus 2x. And now we have one of the variables solved for. What we're going to do is we're going to take this and plug that expression into the y in the objective equation. We could have also solved for x, but it definitely seemed like solving for y was easier here. So let's go ahead and do that. We're plugging that in to here. So let's go ahead and rewrite a equals x times y as a equals x times 2,400 minus 2x. And now for this, before we take the derivative and set it equal to 0, distribute the x. It'll make it a little bit easier. 2400x minus 2x squared. And now we have one equation, one variable. We go ahead and take the derivative, set it equal to 0. So taking the derivative, a prime, or dA dx, however you want to write it, is going to be 2400 minus 4x. We go ahead and set this equal to 0. That's 2400 minus 4x equals 0. Add 4x to both sides. Divide both sides by 4. And we get x equals 600. And then before we go further with this, we have to verify that this is a max, because we're trying to maximize the area. And then remember back to the first derivative test, we go ahead, create this number line, write in 600. You would pick a test point to the left and a test point to the right. So you would pick any number less than 600 and any number greater than 600. You would plug it in the derivative. And if you do that, you would see that a prime would be positive, which means a is increasing for less than 600. If you plug in something greater than 600, you'd see it's negative, which means the function is decreasing. And since it changes from increasing to decreasing at that value, that means there's a relative max at that point. So that's actually one of our answers, x equals 600. Now we just need to solve for y. And solving for y is nice because it's actually solved for right here. All we have to do is plug in for x. So it was y equals 2400 minus 2x. We plug in 600 into x, and that will give us 1200. So our answers are x equals 600 feet. So remember this was in feet, and then y is 1200 feet. So those are the dimensions. And let's go ahead and take a look at what we just found. So we were given 2,400 feet of fencing. We wanted to find the largest area to create using 2,400 feet of fencing. So the combination of x and y here would be x is 600 feet and y is 1,200 feet. That will result in the largest area. So if you wanted to figure out what that area actually is, you just do 600 times 1,200, and that will give you your maximum area given that constraint of a perimeter. Okay, let's do a couple more. A cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. First, let's go ahead and draw a picture. So this may or may not help us, but it's always good to draw it anyway. The picture is a cylinder, so because it's a cylindrical can that we're looking at. So we are told that it can be made to hold 1,000 liters, and that is a volume. So that's going to be, we're going to be having one equation be for volume. And now we have to think, what's the other equation? We're trying to minimize the cost of the metal. So this is actually going to be surface area, which I'm going to denote SA. So kind of a little trick here to remember. This won't always be the case because it kind of depends on what we're maximizing and minimizing. But typically, you're going to have your two equations, as always. Typically, they're either going to be volume and surface area or perimeter and area. So it's either like the one that we're doing right now or the one that we just did. Okay, so one other little trick here. We know that volume is the constraint equation because it says that it's going to hold 1 liter of oil. We want this in the correct units. We want volume written as something cubed. We have to remember two things. 1 liter is the same as 1,000 milliliters. And then we also have to know that one milliliter is 1 cubic centimeter. So 1,000 milliliters is 1,000 cubic centimeters. So something like this would probably be given to you for this little conversion. So point being that volume is not going to equal 1. It's going to equal 1,000 cubic centimeters. So let's go ahead and take a look at the constraint and the objective equation. And this is where we need to know the volume formula for a cylindrical can. Volume for a cylinder is pi r squared times h. It is kind of like a little trick here. The volume of an object is always going to be base times height, where the base is the area of the base. So the area of the base is the area of a circle, which is pi r squared, times height, which is the h. So let's just go ahead and label that too while we're here. This is the radius of that base, and then this would be the height, which is h. And since this is the constraint equation, I'm going to go ahead and just going to erase the v and plug in 1,000 instead of v. Next thing, the objective equation is what we're actually going to be minimizing in this case, and that's going to be the surface area. So the surface area formula is 2 pi r squared plus 2 pi rh. That's the surface area of a cylinder. And now once we have that, once again, we're going to be doing something similar to what we just did. We're going to be rewriting the objective equation so it only has one variable. We need to solve for one of the variables in constraint. It's easiest if you solve for h. So if we divide both sides by pi r squared, we get 1,000 divided by pi r squared equals h. We're going to take this expression and plug it in to the h in the objective equation. Okay, let's go ahead and I'm just going to rewrite the objective equation for now. And we go ahead and plug in for h, so that's 2 pi r squared plus 2 pi r, and then instead of h we have 1000 pi r squared. This cleans up a little bit, the pi's cancel, and then one of those r's are going to cancel. And we end up getting 2 pi r squared, 2 times 1000, 2000 over r. Now we have to find the derivative and set it equal to 0 and solve. So finding, I'm just denoting it SA prime. So the derivative of 2 pi r squared, all we have to do is look at r squared. The derivative of r squared is 2r. So 2 pi times 2r is 4 pi r, right? Because pi is just a constant, so we don't have to worry about that. Next, the derivative of this term right here, you would have to rewrite it as 2000 r to the negative 1 if you wanted to use power rule. And if you do that, you would end up getting negative 2000 over r squared. And now we're going to go ahead and set this equal to 0. So set this whole thing equal to 0. And we need to solve this for r. So I'm going to go ahead and add this term to the right, and we would get 4 pi r equals 2000 over r squared. And now we can multiply both sides by r squared to get it over here on the left. So that would be r times r squared is r cubed. And then in the same step, we can divide both sides by 4r. 2000 divided by 4 is 500. So 500 divided by pi. And then the last step, to get rid of the cubed, we have to take the cube root on both sides. We get the cube root of 500 over pi. So you could type it in the calculator if you want and get a decimal. I'm going to leave it just like this. If you do type it in the calculator, I think you end up getting about 5.42. And almost done. We need to verify that it is a min at this r value. So I'm going to go ahead and write SA prime and SA for the top for surface area. And you could use the rounded value of 5.42 for this, I guess. But when we pick a value to the left, maybe you pick 4, pick a value to the right, maybe we pick 6, and you would see that it would be negative here, positive here when we plug it in the derivative. So that means it would be decreasing and increasing. So since it changes from decreasing to increasing, that means there is a relative min at that value. And now the last thing we need, we have r, we still need our other variable, which is the height. So we can go ahead and go back to right here. Height is 1000 divided by pi r squared. So 1000 divided by pi r squared. We can plug in our value for r, and we would get that right there. And this actually simplifies, if you go ahead and try to simplify this a little bit, it actually simplifies to 2 times the cube root of 500 over pi. This is r, right? We just found that that was r. So the height, when we are minimizing, the height ends up being, to get the minimum value, 2 times the radius of the cylinder. So for our 2 dimensions that will minimize the surface area for this cylinder, r would be the cube root of 500 over pi centimeters, and h would be 2 times that. Once again, for the sake of the notes, you could plug it in the calculator, get out actual values, but I'm just going to leave it just like this. Okay, last one, find the point on the parabola y squared equals 2x that is closest to the point 1, 4. So this one's a little bit trickier here. So we have the point 1, 4. We have this horizontal parabola y squared equals 2x, and we're trying to say what point on this curve is closest to the point 1, 4. So notice here we actually don't have very many formulas that we could be using. It's not like the geometric formulas that we were using in the previous examples. We have to think, what does the word closest mean? That means the distance is going to be the smallest. Smallest means minimize, and we're going to be minimizing the distance formula. So we would have to remember what the distance formula is. The distance between 2 points is, we call it d, is the square root of x2 minus x1 squared plus y2 minus y1 squared. So the square root between the sum of the differences in the x-coordinates squared and the y-coordinates squared. Okay, so next tricky thing here, we now need to figure out essentially why this is useful. We know we're going to have to take the derivative of something, set it equal to 0, and solve. Well, we're trying to figure out the distance between 1 comma 4 and x comma y. So that's going to be d is the square root of x minus 1 squared plus y minus 4 squared, right? Just using this as x1, y1, this is x2, y2, and plugging it in. So the issue is that there are 2 variables still, right? There's still an x and a y. We need 1 variable. We can rewrite this using 1 variable because the equation is y squared equals 2x. We can actually solve this for x by dividing both sides by 2. So we get x equals y squared over 2. And now we can plug this in for the x right here. So when we do that, we get d equals the square root of y squared over 2 minus 1 squared plus y minus 4 squared. And now we're almost past the most difficult part of the question here. Now we have one equation, one variable. We're trying to minimize the distance, which typically would mean take the derivative, set it equal to 0, and solve and verify that it's a minimum. There's one little trick that we could pull here, and that is instead of minimizing the distance, let's minimize d squared, distance squared, because it's easier and it's going to give the same answer. So let's see why it's easier. If we square both sides of this equation, we get d squared, and then on the right side of the equation, the square root cancels, right? And we're just left what was with underneath the square root. And now it's going to be a little bit easier to take the derivative of this and set it equal to 0 and solve. So taking the derivative of d squared is going to be d squared prime. The notation's a little bit weird here, but don't let that bother you, d squared prime. And then the derivative here is going to be chain rule, 2 times y squared over 2 minus 1 times the derivative of the inside, which is just y. Then chain rule for the next term, 2 times y minus 4. And we can, if we simplified this, this actually simplifies nicely. Distribute, combine like terms, you actually end up getting y cubed minus 8. So we have the derivative of the square distance, and we go ahead and set this equal to 0. Y cubed minus 8 equals 0. We add 8 to both sides and get y cubed equals 8. And then we take the cube root of both sides, and the cube root of 8 is 2. Let's go ahead and verify that this is a minimum value here, minimum distance. So we would set up our number line, pick a number to the left, pick a number to the right, plug it in the derivative of the squared distance. You'll see that we get negative and then positive, which means decreasing and then increasing, which means there is a minimum at y equals 2. And let me just move this other stuff over. And now we have the minimum at y equals 2. If we also want x, we just go back up and use the original equation. X is y squared over 2. So I'm just going to go ahead and plug that in. X equals y squared over 2, which is 2 squared over 2, which gives us 2. So that gives us that the closest point to 1, 4 on the curve y squared equals 2x is 2, 2. Let's go ahead and take a look at it. And sure, it looks like this point, the closest point, is about 2, 2 on this curve. Okay, so a little bit different of a question, but same idea. All right, so that is it for this chapter.